This conference will now be recorded.
So today we are going to look again at convolutional neural networks. Well, I think we can skip this part. We did it last time, how an image is encoded. It's like just an image is simply a matrix. If it is one-dimensional, if we have only one color, one component of 4 colors, or for example, if it is we have 3 components like RGB, we will have something like a tensor, 3D matrix. And here we have like 3 layers, RGB. And here it's for each pixel, its coordinates. So we said pixels represent colors, intensities. So grayscale, of course, requires only one color, one channel. RGB is red, green, blue. It's typically what we use in deep learning. There are also others, not just RGB, like lab, HSV, and others. Again, how do we build a neural network that can recognize a cat or this image? How many inputs do we have here? How many inputs do we have?
12,288.
Yes, well, it's written here, 12,288. So these are the inputs. So each input here is connected to a pixel. So each pixel will go to an input. And then we have the first layer here. We call it the hidden layer, the first hidden layer, second hidden layer. And here we got the classes, the neurons that will recognize a class. For example, this can recognize a cat. This one can recognize a dog. This one can recognize, I don't know, a lion, an elephant, and so on, depending on how many classes we want to recognize. So if we have here 1,000 neurons, how many weights do we have inside just in this first layer? If we have 1,000 neurons, so each neuron is connected to how many? It's connected to this number of inputs. So here we have this number of weights plus 1 because we have the bias.
Embryo?
Plus the bias. So we have this number of neurons, of weights. So how many weights do we have here, guys? If we use, for example, 1,000 neurons here, if we have here 1,000 neurons, how many total weights do we have here?
12 million something.
Yeah, 12 million, above 12 million.
12, yeah.
That's quite a lot to recognize just this small image. Quite a lot. 12 million only for this kind of images. And this is almost like a Nikon. It's very small. It's something like this size, or something close to that. Normally, in images that are a lot bigger, for example, like 500 by 500, 500 by 500, it will be 50,000 multiplied by 1,000, which means 50 billion of parameters. That is just insane. Most machines cannot do that. Regular machines. Another challenge we mentioned also last time. If we train a CNN to recognize or train a neural network that can recognize flowers, and most of the data in my data set where flowers are present are in this corner. So will my neural network be able to recognize images that contain the same flower but in different corner? What do you think? Tell me, guys, what do you think? Can we, if my data set, I train the neural network to recognize flowers, but most of the flowers in my images are in this corner. This corner, it means that the features here are different. It's not the same features. It's not the same inputs. My neural network is able to do well on my training data, but when I use images that way, that where my flower is not here, but is here, will my neural network be able to recognize them?
Yeah, it should be.
Not really. If my data set, because this
It's not trained. It's not trained to recognize the flower in that corner.
The inputs here of this pixels in this corner, like we can see them here, are not the same. The pixels that are in here are going to be these inputs. Pixels that are in here are totally different inputs that are here if I use the regular neural networks. So the location matters. If my neural network was trained to recognize like flowers here, it means it has learned to recognize what comes in here, not in here. And normally we don't want that. We want my neural network
to scan all the pictures.
Yeah, to do the same thing across the image.
Mm-hmm.
One solution would be to train a neural network to focus only on a part, and we try to move it around. Move it around like in the image, around the image, to browse like. This is what convolutional networks do to tackle this problem. So, like clearly, like a neural network, a regular neural network, we need a lot of data, a lot of data where we cover most examples. This flower is in here, everywhere, to be able to recognize it. That is clear that it needs a lot of data. So this is just a motivation. How?
Reda, sorry.
Yeah.
So in the captcha, when they just ask us to recognize where is the for example the stairs or the like anything, or car or bus, or is it we are helping them to train some of the models? So, I mean, each time, even if you do it wrong, it would accept it. So is it a way to just train models for, you know, different, like the flower that you just showed us? So each time they just show us different pictures and we just train the models. This is just the way I see it, if you can just confirm.
Could you repeat it, please? I'm not sure I understood.
So when we enter to websites and they check if we are human and not robots, they would just give us few pictures and we would just, you know, select, for example, the cross walking or like anything that they would suggest. I think it's just a way they're using us to train few models.
That's possible. It's possible that
because I tried one time to do. I've done it on purpose. So I've done it wrong on purpose, and it accepted it. So I was just thinking probably they are using us to train the models.
It is possible. It is very possible that they're using people like to train, to like push them to click because they need to click to go forward on the website, and then they actually they are collecting data to help because it costs money to tag data to label them. So I can't say yes or no, but it is possible.
Yeah, I think so. I mean, I might Google it, and I will just say, I will let you know next time. Yeah.
But by the way, there are companies that are specialized in tagging data. It's like you pay them some money, you give them a data set, and they will tag it. Like they can receive like millions of samples, and they will tag it, and of course there is a fee for it. So there are companies that do that, and maybe who knows, maybe they do it for free that way.
Yeah, exactly. Just using customers and just using people, really, random
Yeah,
people.
oh yeah, it's possible. And you know, with deep learning, a little bit of mistakes is okay. It's not a big problem because the quality is not going to be very high, but few mistakes are okay.
Tolerated.
Yeah, they are
Okay.
tolerated with up to current methods. So yeah, thank you, Amal, for this suggestion.
Yeah, I'll just double check it because it's something that was in my mind. I will just double check it and I will let you all know next time.
It is possible. You can do run an investigation.
Yeah.
Thank you. So to continue, convolutional networks are actually inspired from biological systems, from how our visual motor or our visual component works. So what we have, if we run a scan or whatever to look at how our eye is built and the neurons responsible for to build the image, we can see that nearby cells represent nearby regions in the visual fields. So when you have like an image coming to the eye, there are cells that capture the light. So these cells have also like a spatial representation. So each cell that is closer to the other means that they are focusing on the same or on close points. Does it make sense, guys? I think it's very simple, a simple concept.
Yes,
So
like a puzzle.
yeah. Sorry?
I mean, like a puzzle, each one each cell treat the part each cell next.
Yeah, something like
with
that.
each
Yeah, each cell is focusing on a particular point on the field of vision, and they are the same. Like they have the same organization, these cells. So points that are nearby in the visual fields, like this one and this one, will have nearby cells. So they have like the same representation, but that's not all. How it works? So here is the image, and this cell is focusing on this tiny bit. Same in here, same here, and same here. Well, I'm doing this organization just unidimensional, but the cells will be organized in 2 dimensions, same as in here. The cells are organized in 2D. After that, when we receive the information, what happens after these cells, we have all the neurons that comes and are connected only to few cells. Those that are nearby, that represent the nearby, it's like a very complex engineering. It's really amazing. This neuron is connected only to nearby cells, few of them. Another neuron does the same, connected to few of them. So this neuron is capable of recognizing simple shapes. This can recognize just a dot or something very small, or a little bit like something quite small. This one is able to combine them. Like last example, if this is able to recognize something like that, this is something like that, and this is something like that, and this is something like that. If these neurons are capable of recognizing these types of shapes, so this one is capable of recognizing something more complex, a rectangle. But because each one of these is capable of recognizing a type of edge, types of edges of my edges here. So this one is focusing only on this bit, and their combination will produce something more complex, and so on. So this one will be connected to, like we have all the neurons here, and they are connected to another neuron. This neuron is capable of recognizing something even more complex. Say a car. A car is something like this. A very simple car. So this one is capable of recognizing, for example, circles connected to other neurons that can help, basic neurons. And each one, and like it is built in a pyramid-like fashion. First, neurons are capable of recognizing very simple things. Then the next layer is capable of recognizing more complex things, and so on, until we get something. For example, here we can have, if we go very deep, we can have a neuron that is capable of recognizing faces. Sorry for this again. It's capable of recognizing faces, because a face is a lot more complex. It has an eye, the eye is very complex, the nose, the mouth, maybe the hair, and this one will combine them. It's like we have different stages. Here maybe we have a neurons that can recognize eyes, here a nose, here a mouth, here then a neuron that can recognize the top part. Maybe we need to divide them. What is the top part? Then the mouth plus maybe the chin here. And then the combination of all of this at different levels will give me my face. A face is a very complex thing. As you can see here, CNNs tends to be very deep. Normally, when we use feed-forward neural network, the regular neural network that we saw before, it doesn't tend to be too deep. We just have few layers. Generally, we don't go more than 5 layers there. But CNNs, by contrast, can be very deep. We have like CNNs that can go over 100 layers easily. We have that frequently to have like more than 100 layers. Okay, guys? Any questions so far?
Yes, excuse me, Rida. I just want to know what's the output of this CNN, the results.
Yeah, it
Will
depends
be
on the data set.
religions?
The result, well, after we are going to show this example. At the last layer, we get
Yes.
descriptors of what is present. What kind of shapes do we have? So we have.
You mean
here,
texture?
we get a vector, yeah.
A word?
Sorry, what?
I mean word string. I mean
No, it's
as
numbers. It's numbers. We get numbers.
okay.
We get numbers, but we don't know what they are. We get some vectors that tell me what do we have here as numbers, what do we have here. So, but each cell represents something. After this, we build generally a feed-forward neural network, a fully connected layer. Fully connected like the traditional neural network that we have seen before.
Yes.
It means everything, this neuron is connected to everything. Generally, that's how we do things. So this one is what we call a features extractors. It tells me what shapes do we have here in my image, what kind of shapes. Then the fully connected layer will look at the shapes, the different shapes. We'll look at them, combine them, and tell me, this layer will tell me what kind of thing do we have in my the image, in the whole image. And here it's what this output depends on the data set, on what we are trying to predict. If we are, for example, trying to predict just 2 or 3 classes, like cats, dogs, and lions. So we get here 3 neurons. Each one is trying to predict if it is a lion, if it is a dog, or if it is a cat.
Excuse me, just other question. If my image contains many things, I mean, for example, a tree and the sun and complex image. What is
Contain
that?
many
What I
things.
mean? Yeah. So the output will be in the data set. For example, this image will be annotated with the 3 or 4 words. Okay. So this is the output of this
So we can have multiple labels. Yeah, multi-labeling.
Yeah. So it could be with this result, with the CNN, to use it for this.
We
For
can
one
use,
image.
there is no problem. We can use CNN for this. At the output, there is the activation function that we get in the output. If we use the softmax that we are going to see, the softmax will output probabilities. This is, and probabilities, as you know, they sum up to 1. So if this is we have the softmax is used when we need only one output. For example, cat, dog, and lion.
Okay.
And we output probabilities. So if it is a cat, we will have a high probability here. This is called the activation function. But if we have multiple faces here, we can have the 3 of them. We don't use the softmax. We are going to see these examples. We use a sigmoid at every end because we don't need to have we don't have probabilities anymore. They don't sum up to 1.
Yes.
Everything can be present. So this, if I can say so, these neurons will be independent. These outputs will be independent.
But how can I?
You don't use at the last layer. You don't use a softmax. You use a normal sigmoid per output.
Okay.
That's all. Just a simple sigmoid per output. There are other problems. For example, localization. We have, for example, an image. We have a cat here, a dog here, a lion here, and we try to know where they are. Like
localization.
Localization. This is another class of algorithms. They use CNN, but not only CNNs. Maybe on the next chapter or the one after it, we can, or the next session or the one after it, we will see these algorithms. They use CNN in combination with other aspects to determine the localization.
Okay. So if I use the CNN, just I have as a vector of features. This is our result. Is that what do you mean?
Well, at the end we have the classes. We have the classification. But here we have what we call the vector of features. It tells me what shapes we have in here.
So if I want to use just a feature of the image, I can use the last before last layer. Is that?
You can extract this layer. You can extract
it.
And you take but the thing is, it's not you who define it, this layer, the feature layer.
What? Yeah.
It's not you who defines it. You do define it, sorry. You don't define it. It is learned automatically. It's hard. There are ways of knowing what this represents, but it is not easy to know what this shape is, what this shape is. It's because backpropagation determines what shapes are required to understand, to know the class. By backpropagating, what happens, each neuron will try to learn something that helps the whole network to understand, to be able to classify if it is a cat, a dog, or a lion. So it's like the whole network is cooperating. We have a lot of neurons here, millions, as you can see, of weights, cooperating to know what they should learn, to be able to recognize cats, dogs, and lions. And if we do, there are ways of reverse engineering each neuron, what it is doing, what it is learning. We will find each one focusing on a particular shape. Here we can find sometimes that this is for focusing on rectangles or on faces or on ears, things like that. Here maybe it is focusing on eyes, because a lion eye, a cat's eye, and a dog's eye are different. So this is able to recognize that. So, and they are all cooperating to know what each should be specialized on. And this is done automatically, like by magic, like the backpropagation, just by the inputs and the outputs of the data set will allow this whole neural network to calibrate itself by backpropagating the information. And well, this is what we call training. And something that can recognize these things.
Yes, sorry, Rida. In the vector, do we have all the features or only the features that we need for the specific image?
Yeah, mainly or only those that matter.
Okay.
Of course, because the neural network is trying to optimize something, the error, reduce the error here to recognize cats, dogs, and lions. So of course it will try to focus on only the features. For example, if we are trying to recognize only lions and cats, and the lion eye and the cat's eye are the same, then it won't focus on that. Maybe we won't even find eyes here.
This features is like, look, I don't know, color and texture and shape.
It's a group of pixels, basically, a number of pixels.
So it will be different when we take the image and we extract all this feature by using, for example, color or texture or shape or.
No, it will use everything. A texture is just a number of colors together, grouped together. So this is focusing on, because this is focusing on some parts of the image. This is focusing, because it's connected to here, it is focusing on here.
Mm-hmm.
This one is probably focusing on something a little bit big, like here. And it is trying to recognize if it is yes or no, for example, a eye, by this combination of these neurons.
Yeah.
Try to recognize if it is an eye or not. Maybe this one is trying to recognize a mouth. It's connected to some neurons, with each one specialized in a portion of the mouth. And this is trying to say if we have a mouth here or not.
But it take all the features. I mean, a combination, I think, of features of texture and color and shape.
Of course, this one, for example, this neuron is taking all the pixels and all the colors, all the RGB components.
Mm-hmm.
Well, but a texture here is not like in traditional machine learning or traditional image vision.
Yeah, is that what I mean?
Where we had texture, and every texture is just a bunch of pixels that are grouped together. In traditional like image processing, we'll try to localize textures, which means just grouping some bunch of pixels. But we don't need to do that here. Here this is just focusing on a rectangle of pixels, for example, 3 by 3, just a little bit.
But
just a little bit, a small region. Same in here.
Okay.
So we don't have this notion of texture. We don't try to, for example, if we have a lie here, we don't need to run a texture detector and to get us the eye. Then we put it in a machine learning solution to recognize if it is an eye or not. This is not required in CNNs.
Just they base on the shape, maybe.
Because only it's based on stacking. A texture is just a stack of different small regions. So it is stacking things. Stacking. This is focusing on a small thing. This is a small thing. I'm going to show you the convolution, how the convolution works to detect if there is an eye here or not. This is the convolutional, like how it works, because it slides. Let's see that, and then you will see why we don't need to recognize textures in these cases.
Relu, sorry, one question. So far we've talking about images. I assume it to be just static, so images that do not move, like cat, dogs, lions.
Yeah.
Would it be different? Would CNN be different for animated objects?
Yeah, videos. Yeah, they will be different. Okay. There are
How different? Is it very different?
There are multiple ways of doing it. There are, for example, a way where we sample different images of the video at an interval, and we run a CNN in all of them. A CNN on every image of the video for every image, and then we add another layer at the end that can group the information for every image. So we have multiple images. There are ways where we can stack a NN at the end. We have multiple CNNs for each image, and we add a NN that can also combine them. So there are multiple ways, and it is a hot list, more or less, research area that is trying to figure out what's the best way to do video classification. We do quite a lot of that in my team, like to do video classification.
Okay, great, thank you.
Any other question, guys? Let's see how it works. For example, the first layers here are recognizing edges. Edges are just vertical and horizontal lines, if you look at them. Then we have another layer that is combining these edges to recognize eyes, for example, nose, mouth. And then, as you can see here, combination of this leads to face. Combination of this leads to face. Okay? Okay, guys?
Yes, yeah.
So here we have one of the earliest forms of CNNs by these guys. This is these two guys are especially known to be like legendary guys in machine learning or in deep learning, Jan LeCun and Joshua Bengio. So just to look at some history, we have here like an image, a convolution. Then this is focusing on only this bit to recognize, for example, this K. So this is recognizing like tiny shapes. Then this is combining other shapes, and so on. And here we have got what is called fully connected layer. After that, we get our classification. Let's see, we will see how this works. Because a shape, a particular shape, for example, this kind of shapes, this kind of edge, it's the same everywhere. An edge is an edge. So we don't need multiple neurons to recognize it. Yes? Yes or no?
Yes.
We don't need multiple neurons. So we can use one single neuron that can recognize a shape like this edge, and slide it. Because this shape is very small and the image is very big. So we have this neuron capable of recognizing this shape, and it slides like here. It keeps sliding. After it slides, how many outputs are we going to have? So we have here a number of inputs. A normal neuron have multiple inputs, and how many outputs? A regular neuron.
One.
Only one, exactly. It has multiple inputs and one output. But here, how many we will have?
Many, depending
Exactly,
on
many.
number of slides.
Exactly, we will have many. We will have many outputs. This is one of the things that can allow me to slide and to train only one single neuron to recognize a shape like this and generalize it across all the image. It's like it's trying to look for it. Where do we have a shape like this? Then well, such a neuron has this information. This is the image, 32 by 32 by 3. And here we have what we call a filter. A filter is just a small region. How many like pixels we are my neuron is focusing on? 5 by 5, 3 just for the number of channels. RGB, you have 3 colors, so each pixel has 3 colors, 3 components. So it is here, it is focusing on 5. And we call this operation convolve. That's why we call it a convolutional neural network. We are convolving, which means we are sliding like that all over the spatial locations. And this is called what we produce. To simplify things, this will say if we have this shape or not in here. So it will be something like 0 or 1. 0, 1. When we have 1, it means that we have the shape. When we have zeros, it means we don't have it. And we have what we call the activation map for all the image. This will just tell me where we have the shape and where we don't have it. Okay? We can add another neuron that is specialized on another shape like this. And this neuron will tell me where do we have this and where we don't have it. For example, again, zeros and 1. And it will tell me where do we have this shape or not. This is the same for another shape. So each neuron is going to slide, or we can call it a virtual neuron, and produce this activation map. The previous neuron, the blue one, did the same thing, and we can have multiples. At the end, we end up with something like this. We end up something like this. So each activation map is connected to how does it need many neurons or just one for each activation map. Here we have 6, only one neuron. And each one is specialized, is telling us what we have, where we have a particular shape in my image. So here we are looking at 6 different shapes. So after the convolutional layer, after the convolution, we generally add a Relu. A Relu is something like that. A sigmoid, if you remember, is like that. A sigmoid is like that, 0, 1. So anything that is in here will become 1, and anything that is here will become 0. So here we have 1, and here we have 0. The sigmoid is something that divides my values. Big values will become 1, depending on where we are here. And small values will become 0. But values in here, in between, can be very small. The difference I mean between them. Here you can see that the gradient is very small, the gradient here. Can you see it? Can you feel that the gradient is changing very little here?
Yeah.
And what we said about small values for the gradient or big values. If the gradient is very small or there is very little change to it, when we multiply them, what will happen? Depending on the loss function. What will happen when we multiply small values?
It tends to get smaller.
And it can, what effect will we have when we have a lot of layers, each one with small values for their gradients?
Becomes 0. It goes.
Yeah, and how did we call that problem? The
Vanish.
Yes,
Vanishing.
vanishing gradient.
Vanishing.
The sigmoid is not a good choice in this case. To tell me, the sigmoid will tell me, for example, when I have a convolution layer, it will tell me if there is a shape or not. It transforms the value on 0 or 1. Does the shape exist here or not? 1 if it exists, 0 if it doesn't. So we don't use a sigmoid generally in convolutional neural network. We use the Relu. Relu is something like this. So every value that is negative will become 0. And every value that is positive stay the same. Here, x and y. X equals y here. So every value that is positive stay the same. Every value that is negative is removed. It becomes 0. It doesn't transform into 0 or 1. The 0 is 0, but positive value remains the same. The gradient here is better. As you can see here, here it's not good, very good, but here it's better. The gradient here, we have some gradient. It's not a very small value when we put it in conjunction with the loss function. There is a more advanced concept, but I will explain it later. So this way, when we use the Relu, it's one way to avoid, because we said that convolutional networks tends to be very deep. We have a lot of layers. And because we have a lot of layers, it's not wise to use the sigmoid activation, the thing that transforms 0 or to 0 or 1. So it is wiser to use. You should give me ask me a question here, guys. I know it's a bit too early, but you should ask me a question. We said that a sigmoid should be what? Derivable. An activation function should be derivable, because in my whole neural network, we are trying to compute some derivatives, yes or no, of the loss function.
Yes.
So we have a loss function equals something. The loss function should be derivable to compute the derivatives. But this is this, and this is here inside. It is either a sigmoid or some activation function like the Relu here in the formula. Is this derivable or not?
Maybe no.
No, here it's not continuous. Yeah, it's not derivable here. This is if x is smaller than 0, then y equals 0, else y equals x. This is clearly not a continuous function. But it's not a big problem. We can just approximate a value. It's not continuous in a tiny point. We can use derivative here when we have a point here, and the derivative here when we have the pointing here, and it is fine. We don't need something that is because points that will come exactly at 0 are very rare. That will come exactly here in the uncontinuous thing, and we can use anything like to bypass this problem. So it's not like a big problem when we have this continuity here. Is it clear?
Sorry, Rida. So regarding the 0, is clear. It's like we can round it directly to the 0 when we have like small values. But for the positive, how we can count the loss function here?
The loss function is just
it's not derivative.
A loss function is just a combination of multiple functions.
Yes.
The Relu is somewhere here. Relu of some input of this convolutional layer output, sorry, and we apply the Relu to them. So computing the Relu is not a big problem. If it is below 0, it is 0. If it is above 0, we keep the same value. We don't change it. What is the problem is the derivative. Because the Relu is not continuous, so we cannot, it's not derivable here. But it's not a big problem, because we can do the derivation when we are here according to this part. And we do the derivation here according to here when we are here. It's very rare to find ourselves exactly in 0 and try to use the derivative here in 0. It's because, as you can see here and here the gradient is very hard to determine. It's not continuous. Is it this way? Is it this way? Is it this way? There is no clear slope here. We can have multiple gradients. If we use this, we have this gradient. If we use this function, we have this gradient. It's like the gradient is not clear how it is going when it is discontinued. But even that way, it's not a big problem. We can it's very rare to have data points from the data set that will be exactly in 0. Sometimes they will be a little bit here or a little bit here. So this is not like a major problem. Does it explain it, Miriam?
Yeah, I got it. So when we have this problem, it's like now it's not clear. We're gonna round it to 0 or I don't
No,
know. It's like
it happens very rarely.
Mhm.
We don't round. We don't have to round it.
The
It's like
derivative. Yeah, I know the derivative. So which sense it goes?
yeah, if it is exactly 0, it's a bit of problem, but we can use
Mhm.
anything. We can use this derivative or this one. We will have a different gradient, but it's not a big deal. It's not a big problem. If preferably we use this one, the one that is
So it goes in
some
the
information.
positive side.
Yeah,
Mhm.
but it's like very rare to have exactly 0 here. The
Okay.
data sets are generally a little bit, we get 0.1, 0. minus 0.001. So it's not like, it rarely occurs to have exactly that value. It is because it's discontinued exactly here. If we move slightly left or right, it's not no longer, it's still derivable there. But here,
Okay.
it's like, yeah, the gradient is not clear. So this is just to tell you what's the problem with the Relu, but it's not a big deal of a problem. The sigmoid is better in that sense because it's continuous. The gradient is present at every point, but it has like these little values here that can produce the vanishing gradient. Okay?
Okay, yeah. Thank you.
Let's go now. Let's simplify things now again. So what we are doing, we have a convolutional layer. A convolutional layer is producing some feature maps. Feature maps are telling me what shapes do we have at each level. Then the Relu tells me if it is negative, the shape is not present. If it is a high value, it means the shape is very present, very much present. This is the definition of what we get in the feature maps. So we have here a stack of feature maps, which is this one. So we have multiple feature maps. Before, what we said if a feature is present, we put 1. If it is not present, we put 0. With this activation function, it's not the case. We put 0 when it is not present, but we put a number telling us how much is it present. Because, for example, if we are looking to an A, this is an A. This is a bit of an A. So shall we put 0 for this or not? We can put a high value on here because this is clearly an A. For example, say 10. And we can put a small value here, 5. This looks like very much like an A. This looks a little bit like an A. This is the effect of the Relu function. It tells me in the feature map how close we are to the shape that we have learned. So it's not 0 and 1. It's no longer binary. It's more of a percentage, like a degree of like how close it is to that feature. For example, this, if we are trying to look for this edge, if in the image we have something like this, this is very similar to this. Do you agree, guys? But this is almost similar to it. So we get a high value for this, but smaller value for this, maybe a 2 or 3, 2, 3. Here we can have a big value 10 because it's very, very close to this. So this is what the Relu function is going to do. It tells me how close my shapes are to the shape that the neuron has been trained to recognize. Is it clear?
Yes, yeah. So the Relu is like more specific than.
Yeah, it gives me a degree of closeness. It's like a distance measure, more of a distance measure. It's better than the sigmoid will give me a distance measure, but it's more binary, almost like 0 and 1. The Relu will give me a bit more, and it has a better gradient. So that's the advantage of the Relu and why we use the Relu instead of the sigmoid. Okay? Are you all fine with this?
Yeah, so that means the accuracy here is gonna be like 80%, something like this, since it doesn't give the exact shape.
A kind of value, yeah, big value. It's not a percentage, but it's a big value is determined big closeness and to that shape. Small values means it's very close, like it's close enough but not too close. And negative and zeros means it is like not the same at all.
Okay.
So it's better to have this like degree of closeness rather than a binary thing, 0 and 1. It can generalize better. It gives me how close I am to that shape. Okay, are you happy with this explanation, guys?
Yeah. So Reda, I'm just trying to see how can we use the degree, which is like low. So if, for example, for the A that was like 5, are we going to rely on this, or we just?
Yes, the next neuron will rely on it.
Even if it has like a less mark or like a degree.
Yeah, it will determine when it stops with the bias and these things. It will determine when it should take it into consideration or not. We have the bias, that B value in each neuron, and this one will determine when it's going to stop or not taking it into consideration. Like, so the next neuron is taking different shapes, trying to combine them, and C determines if a closeness degree is acceptable or not by taking these values. Does it make sense, Amal?
Yes, yeah, thank you.
Any other question, guys? Please stop me, because these are like very important concepts. So then what we do in the convolutional layer, we stack different convnets. So we have, here is the image, then we have a convolutional layer with a Relu. We say that we are using a filter of 5 by 5 by 3. What does it mean, guys, this 5 by 5 by 3? Tell me. Tell me, guys, what does it mean? 5 by 5 by 3?
3 dimension?
What is 3 dimension? What does it represent?
Maybe like the height. Width.
No, this one represents the number of channels.
Oh.
3 colors. And 5 by 5?
X and Y.
Yeah, how big is my kernel? Like, my neuron is focusing on 5 by 5, slide in. It will slide and try to into zones by 5 by 5. And 3 is the number of this one is the number of channels, which means RGB. Then we have this Convnet plus a Relu to put some threshold when we have a shape and when we don't have it. Then we have another layer. We have this feature map produced. Another layer comes and try to take this feature map. Here we have 6. What is this 6? What is this 6, guys? Tell me what is the 6?
Colors.
Not colors, no. We no longer have colors here. Here we have colors. Here what we recognized?
The number of shapes.
Exactly, that's the number of shapes that we are trying to recognize. That's the number of shapes, yes. So here we have 6 dimensions here in my feature map. 6. It means we have like something like 6 feature maps. This is the number of shapes. Each layer here is focusing on one particular types of shapes. So how many neurons do we have here in my Convnet? How many neurons did we? Each neuron is specialized in one type of shapes. So how many neurons do we have?
6.
6, perfect. Then we do the same thing again. So this one is taken as an input shapes. Here we just took points. Sorry, we took shapes, but small ones, 5 by 5. Now we are actually taking 5 by 5 by 6. We are obliged to take 6. So it takes 5.5.
Reda, how are you guessing that 3 is color and 6? Maybe I'm just missing the point. Like,
because in the beginning we have only colors as channels. We don't
okay.
have anything else. We have just colors.
And then how did you guess that 6 is number of shapes?
It's because these neurons will output, each neuron will output a layer of the feature map. Its dimension is 28 by 28 by 1. It has only 1 dimension here. And 6, it means that we have 6 feature maps. And of course, if feature maps is specialized in a particular type of shapes, so 6 here means 6 feature maps. Does it make sense for you, Emel, or not yet?
It's fine. I mean, you can carry on if it's not clear yet. But yeah, I'll just
okay,
probably ask you questions.
Let's look at this.
Yeah, it's not clear for me either.
Yeah, tell me, guys. I know it's not going to be clear, these things. Nobody can, or most people cannot understand these things the first go.
So the first we have always a 3 is the number of colors, right?
Exactly.
And after
First, exactly.
always a 3. Okay.
Yeah.
And the second, depending on the output of the, of the first layer, it can be more than 6. It means
it can be any number. Yeah. Generally, we put it. We select this number.
Mm-hmm.
Exactly, like Miriam said, Amal, the number of channels in the beginning is always 3. The image is always most of the time has 3 components.
Yes.
RGB. Then after that, we no longer focus on colors. We focus on shapes. So we produced, with 6 neurons, we produced here 6 activation maps or feature maps. We produced 6. So each one of them is recognizing one type of shapes. Could be something like this, could be this shape, could be this, could be this, could be something like this, like half a circle, or this kind of things. Because of this, what we get after this is always here the number of shapes that we are trying to recognize. We don't have anything else. Okay?
Yes, yeah.
We don't have anything else. It's just the number of we get for each neuron, we get 1 activation map. So if we have 6, we get 6. The color is only in the beginning. After that, the color is inside this. A particular shape has a color inside of it. If it is either it is black, or it can be red or blue, it can be anything. We can have, for example, this layer recognizing a red edge, and this one recognizing a blue edge. It is possible to have this same form but different colors. So colors now are inside of these neurons. They are taken into consideration to recognize the shapes. And then we get for each one the activation map. After this, so here we get some shapes.
Sorry, the second layer, sorry. So the second layer depends on the complexity of the shape and the colors. It's like both.
Both, yeah. The shape and the colors, yeah.
Okay, so
exactly.
More the shape is complex, more we have more maps. Is it correct?
Yeah. If we need a lot of shapes, we will have more activation maps. Yeah, more neurons, and if we need a lot of different small variations on shapes and colors, if we need that, we will need more here. This number.
And if it has also a lot of colors, it means we need more activation maps.
Possibly, yeah. Depending on the classification, what we are using, yeah, it's possible that we need more.
Okay, correct. Thank you.
And here we are having now some more shapes, and we get another Convnet. This is taking now shapes, different shapes in different colors, colored shapes, and trying to get what is this? What we got here? Tell me what we got here.
Hidden layer.
Sorry, what?
Hidden layer.
Yeah,
Another
they
layer.
are all hidden layer, but this is like the activation map. This is another activation map. But what does it represent?
So the shape, I mean the image, no?
There is no real image now. It's more of a bunch of shapes here.
I mean the whole shape, the whole image. For example, as you show us before,
something more complex. Yeah, more complex.
the face, for example, the face or something. Yeah.
So here maybe it's the edges. Now we are having maybe eyes. But as you can see here, how many do we have of types of shapes here? Complex, more complex shapes. How many?
10.
How many? 10. Yeah, the image is shrinking a little bit. I will tell you why after this. And now we have 10. Why? You can see that the number of shapes as we increase in complexity. So this is more complex shape than this one. Amali, do you agree?
Yes, yeah.
And this is a very simple. It's just pixel level. So the more complex we go, you can see that the image is a little bit shrinking, but we have more channels. Here it was just 3, now 6, then 10. Why do you think is this? Why do we have more channels as long as we go high in complexity?
Because we are combining what we learned before, so they know more.
Yeah, we have a higher degree of combinations. We can combine more. Here, if we have just 3, we are going to combine different organization of pixels, and we get more variations. We get more variations of the same shape, of the different shapes. Then we have here 6 different shapes. We go to the other level, because we have 6 different shapes, combining them will produce even more complex shapes. The number of combination is higher than here.
Yes.
So the more we have like this in this channel, we have more values in this channel, the more activation map we have, the more possibilities we can build. Complex objects can be built with more variations. An eye can have multiple forms. We can have a mouth here. We can have a nose. We can have ears. We can have chins. We can have a lot of things here. But here it's just very basic shapes, horizontal and vertical lines. And combining them will get me in different ways, will get me more possible shapes. Then if we go to faces, for example, here, if we are looking for faces, we will have even a lot more here. We will have a lot more than 10. Because faces, like we are, guys, we are also trying to see faces that don't even exist. Like we can have multiple mouth, multiple eyes. It's a bit funny, but we can have that, these combinations. And we will have like even like a lot more complex shapes. So the higher we increase the complexity, the more we can, or the more variations we can build. And the number of channels or activation maps will be higher. Okay?
Okay.
So this is what this 3x3 filters mean. Before we said 5x5, for example, here, but generally we use a lot this 3x3 because it's very small. So we have 3x3. And then what we call convolve is that we slide. So we have 3x3 here, and we slide. We call this is the stride. It means we slide by 1. So we are here, and then we jump to the next position. It's like this one and this one are overlapping. We need this overlapping because we don't know where the shape starts and where the shape ends. So we need like to scan in that order. We need to keep scanning for that particular shape. So we move here by 1 because the stride equals 1. Then we move here, then we move here, and then we move here. So how many values do we have here? 5x5. So here it is 1 value for this. The neuron will produce 1 value here. Then we move, we get this, and if we move again, it's 5. And then we do the same thing again. We move a little bit down here, and we keep doing the same thing again. until we get 5 by 5. Are you happy with this explanation? How we are sliding?
Yes.
It's clear.
So Reda, with the one thing I don't understand, I got how you moved it, but how do we get 5 by 5? I'm not quite sure. Can you explain that again?
It's because how many values do we have here? So this is one value. We move again, one, another, the second one, third one, fourth one, and the last one, we move here, and we get 5 of different values. It's 5. When we reach
How
the
many
end,
times you move is 5, basically.
yeah, along the horizontal line, it's 5. And same goes in the vertical line, vertical axis. We are going to move by 1 here, then 1, then 1, and we move 5 times. So we get like 5 by 5 outputs. Is it clear?
Yeah, thank you.
For all of you?
Yes.
We are the one who set the filters. It's like here
Exactly.
we are 3 by 3.
Exactly.
So
yeah.
So it can be higher.
It can be higher, yeah. It's not advisable.
So that means the output change.
Exactly.
You change. Okay.
Exactly. And you can even change the stride. Although it is not like recommended.
Oh.
Like, yeah,
The
3
best
by
is
3.
1?
Sorry?
The best one, the best stride is 1?
Generally, yeah, in most cases, it's very rare like to have 2 or more. Generally, it's 1 because we need to scan along this. Well, if we use 2, we will get less outputs. For example, the feature map will be smaller. It will be not 5 by 5 if we use a bigger stride. But we might lose something.
Maybe if the picture is too big, we can go for.
Yeah,
like,
we can. Maybe you can do that and see what will happen if your accuracy is still good or your performance meter is not dropping.
But we can play on the filters in this case, for example.
Yeah, we can play with the filter. Yeah.
Okay.
Well, big filters will also. That doesn't mean that you are going to get smaller outputs. Because big filters, we take this and you will move by 1. It might like reduce it a little bit, but not by much.
Okay.
But remember, big filters mean we have more weights because each neuron will be connected to more inputs. So we get more weights that we are training. And this adds to the complexity. Okay?
Okay.
Are you sure or hesitating?
I'm not hesitating, but it's more clear. It's normal that more filters. What is the best, from your experience?
Yeah, 3 by 3 is used most of the time. Maybe 80% of the time we use 3 by 3.
Okay.
We are going to examine possibly on the next session different architectures. We have a lot of architectures, famous ones that we can use, and most of the time they use 3 by 3. Sometimes in some layers they use 5. 7 is probably the maximum. 7 by 7 is the maximum, but they rarely use it. Most of the time it's 3 by 3. Okay. We are going to examine them and stride of 1.
So Reda, is this all for 2D images?
Yes, these are mainly used for 2D, not just images actually, just any 2D
just
representation.
2D,
yeah.
Yeah.
Actually, if you know, when Google did the DeepMind team, I think they used chess. That how do you call it? AlphaGo, the one that beat the world champion, if you remember it.
Yeah.
It's not an image. The Go is a board, and they use the convolutional neural network, part of the whole architecture, to determine like what's the best move to play. Because the board game is like a matrix. It's not an image. It's just a matrix where we have pieces. A piece like what we are going to play, the piece that is part of the game, and they represented it as a matrix, and they use convolutional neural network, although it is not an image. So CNNs, in this types of CNNs, can be used for images because images are matrices, and can even be used in things that are of different dimensions. For example, text. In text, we tried CNNs. CNNs can be used for one-dimensional data. It means that when we do the filter and when we slide only on one dimension. For 3 dimensions, it also exists. Okay.
Sorry, Reda, if I'm understanding. About text. There is 26 in place of 3 of RGB. I mean,
the number of filters, that's a different story. No, it's not that case. I will give you an example when we reach text. It's basically the embeddings that we use for text. It's not it's not the number, the different types of characters. We don't really use that, like how many variation of characters like we have. Because like one character is not a combination of multiple characters. It's just one character.
Exactly.
We have different ways. For text, it's a little bit different. Yeah, we have other stuffs. We are going to study it deeply when we reach it, because in my opinion, text is harder to understand than images.
Okay, thank you.
No problem. So here we have the stride equal 2, and you can see here we jump by 2. It's not moving by 1, but jumping by 2. So we got less. 3 by 3 outputs. Again, stride equal 3. We can use it. We can jump here. So 3, we go here. Then we move here. After we move here, we cannot move here. When we jump here, with stride equal 3, we need 3 other things to move here. This is almost like ignored. This is a problem. So some strides or some configuration, depending on the filter, will be a problem. We cannot do it. This is a problem. We cannot. So what we do to avoid this thing, we use what we call padding. We apply padding. So we add zeros around. So that way, when we use a stride of 3, so we jump here, then here, then here, then we have no problem. This is a simple solution when we add zeros around the image to make the convolution easy. It's a very simple thing. So just to have the numbers that sum up. So this can be like divided by 3, and we can jump and cover the whole image. So we call this zero padding. Is it fine? Is it fine so far, guys?
Yes. Yes, yeah.
Yes.
So this is the Relu. I think we talked about it. Well, this is just some recommendations. In practice, we use strides typically of 1 value. 3 by 3 is also used a lot, most of the time, for the filter size. The Relu is the activation function. Yeah, we explained it. We have also what we call, this is a simple concept, very simple one, what we call the max pooling. The max pooling, it's just to downsample my filters. So this is one filter. It's a particular shape that we recognized here. One activation map, just one. We can do what we call the max pooling. The max pooling, we subsample. For example, for each value, so we have here my feature maps. A feature map is specialized in what? A feature map is specialized in what? Tell me, guys.
It's an output of a filter applied on the previous layer.
Yeah, but it recognizes one particular shape. One feature map is specialized in one single shape. Yes or no?
Yeah.
Yeah, a feature map, like we said. So each neuron produces one feature map, and each neuron is specialized in one type of shapes. So each feature map tells me if a particular shape is present or not. That is what we said about feature maps. Do you all agree, guys?
Yes.
Perfect. Now, what this represents, what these values represent? We have 5 here, 1 here, 10 here, 0 here. What does it represent? Say this feature map try to recognize circles. So what does this value mean? What do they mean? What 1 means, what a 5 means. This feature map is for circles. Say, just so what does the 5 mean, 1 mean, 10 mean, 0 mean? What does it mean?
Is it the Relu result?
It's yeah, of course, it's the output of the Relu, yeah.
So
After
it means a specific shape.
hear.
For example, if we have 5, the number of shape.
Not the number of shapes, no.
I mean,
Probability we have this feature in that place.
And what's the difference between 5, 1, and 10 and 0?
So if we have a higher number, we have a higher probability, something like this.
Perfect.
So it's taking the maximum value of each,
Yeah. If it is a high value, it means it's very close to a circle. If it is a low value, it means it's very low, like it's not similar to a circle. And these feature maps, these zones, are closed spatially. So this feature map is like connected to an image. We have an image here, and it is connected to a feature map. So a feature map like that means that the pixels that produce this are close to the pixels that produce this. They are spatially closed. Do you agree with me?
yes.
They are closed spatially because when I slide, I keep the same order when my neuron slides. So this one can be like if we have a side of 1, they can like overlap like this. This is for this, and this is for this. They can overlap. So what we do with the max pooling, we take the maximum between these 4. The maximum is what here? 10.
10.
So what happens? We remove all the others. The matrix will be smaller. And here we have 10. Why do you think we do that? This matrix will become a lot smaller. Like, yeah, yes, Pharaoh?
Maybe for sizing to recognize a bigger shape with the same pattern, but it's bigger. Or maybe
you are close to it. Yeah, you are close to that. Yeah. What happens is because we try to see if this circle is present into this location. So if it is not present, we can ignore it because it's present. It's like we lose precision. We lose precision. We know the circle is here, but we make it in here by making it less precise. So we lose some precision, but now first my feature map is smaller. That's the first thing, which means we made it easier for the network to train because we have now less weights for the next layer. The next layer will be connected to a smaller feature map. In the beginning, it was like that. Now it became a lot smaller. 220, 224. By 224, now it was divided by 2 in each dimension, which means it was divided by 4, like this, just a quarter of it. When we do that, when we go from here to here, it's like we divided it by 4, just a quarter of the feature map. That's the first thing. The next thing is that we are going to generalize better. Why? Because we are looking at the maximum in these 4 values. If my circle doesn't exist in here, or if the circle exists in one of them, we are saying it's the same. Do you have a feel? Do you see the feeling? Your feeling about this concept? So if the circle is here or here or here or here, we tell the network is the same. If it is slightly different, because if it is slightly moving left or right, it's still a face. if the eye is moving slightly, just a little bit to the left, right, top, bottom, slightly moving, it's still a face. It doesn't make a big difference. So that way, we make the network generalize better. We tolerate some variation but just a little, some variation in spatial positioning. But it's not perfect for resizing. It's not really good for resizing. If the eye is big or small, it doesn't really tackle this problem. We have to make the dataset bigger for these cases. But does it make sense for you guys?
No, Reda, sorry.
That's fine. That's fine.
Why is it good to take the maximum value again? Why
Yes.
are we taking 10? Why we don't take the average value?
Yeah, it exists, by the way. It exists. There is the max pooling and the average pooling.
Okay.
They both exist. I tend to use more the max pooling. Some other applications use the average pooling. Why do we use the max? Just to say that if this circle is present here, 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 or here, is the same thing. We want it to be tolerant to small variation in positioning. For example, we are in a face. We have an eye here and an eye here. If the eye moves a little bit here, or here, slightly moving, or here, or here, it's still this. We can say it's still the same person. We should tolerate it. Small variations in positioning should be acceptable. That's what we mean by this. So if we find like the eye here is 10, if we move a little bit, it's still a 9. Yes or no? So we have a 9 here. If we focus on it, when we slide, we are here, it's 10. If we move a little bit here, it's say 5. It's a 9, but not as close, not as good as the other eye, as this 10. So when we see that, we say also try to ignore other things that are close to an eye, that are close to it, and just focus on the one that is that has a higher score. Because others maybe they are representing the same eye, but with slightly less information. So maybe this 5, this 1, and this 10 are the same eye, but with slightly different variations. So we tell the network to focus only on this, on the highest value, and we remove the others. Because this eye, because it's the same eye, this eye as a whole, and this eye without this bit is the same eye. Amal, yes or no?
Yes, yeah.
But because the convolution is focusing only on this bit, and the previous convolution, this 10, is focusing on the whole eye, it is getting a higher score. So we can ignore this. We can ignore this. Yes or no?
Yes, yeah.
And just take this information. This is the max pooling, what the max pooling is doing. It tries to ignore things that represent the same information, but slightly different. It's the same information, but just a little bit different. So ignoring them is not going to harm us. And what it does, we are not obliged to do it, by the way, but it shrinks the network by a big amount. It shrinks the feature map by a big amount, and it makes the training faster. And also, it makes things more generalizable. It generalizes better because we are looking just at an eye in the neighborhood. We tolerate some errors. So this is why the max pooling is able to help, and it is recommended.
Rita, sorry. So at the beginning you said we use max pooling when we have like two close value, for example 5 and 10. But like for me 1 is far from 10. I don't know why.
Yeah, because when we move, for example, here, maybe we have I don't know. Sorry, when maybe we have a nose here. When we move a little bit, it's no longer an eye because it's a mixture of a nose and an eye. For example, if we move here. But this feature map is specialized, say, only on eyes. We have the other feature maps for noses. Yes or no?
Yes.
A feature map is specialized only on one thing. We have the one for noses, that is dealing with noses. So if it is specialized only on eyes, and we have an eye somewhere here in this neighborhood, here if it is a 1, it means we don't have an eye. It means there is something like look like an eye, but it has other things that makes it like quite different. So what we are saying here, if we remove them, there is an average pooling. It exists and it is used in many cases. But what we are doing here is to say if there is a my here and nothing there, just take the maximum. It's like ignoring the other places. And if the I is present in here, we do the same thing. We ignore others and we take this. It means that if it is tolerant to positioning. If the eye is moving slightly, like in the neighborhood, it is here. Because when you take image, there is sometimes noise. There is the way how you take the picture. There is always these differences. So if you make it a little bit tolerant to the position, the eye is here or here or here or here, we tell it it's the same. So, and because this is specialized only on eyes, it doesn't care about other information, it tends to work. Because other information, if this is a 1, it can be a nose here. We have the feature map that does the same things with noses and with mouth and etc. So we can afford to reduce the size and take only the maximum, because we are focusing on if the eye is present in that neighborhood, not exactly on that spot. It's not how images works. Images have some approximations. We are not looking at exactly the same spot. We look at the eye. When we look at the face, you expect the eye to be at a certain position, not exactly in one spot. Yes or no?
Yes.
So this is how I intuitively explain it.
Yes,
Are you happy, guys?
We have here there is a small problem. For example, just imagine we have this feature map is for eyes. Okay, very good. Just think if we have like a small face with the 2 eyes, and the original eye is bigger, and here we have like the neuron or this future map. It said like we have like 2 eyes that are near to each other. So in this case, if we do the pooling, so it means like we will ignore one of these 2 eyes.
It doesn't really happen like that. It can happen for very little cases. It's because here, if you are using a small slide, this image and like this pix cell and this cell are like overlapping, because we are convolving. This cell and this cell are overlapping. We are not jumping. The slide is not jumping from the one eye to the other eye. They are overlapping like we did here. You see that?
I get it.
They are overlapping. So this overlapping allows us also like to do this. We are scanning, and then it's like to make it simple, we are scanning for the eye with like this. We are scanning for it and taking the one that is highest in values. Something like that. Does it make sense? We are like scanning for the eye and keeping the one that has a high value and close to, and removing the ones that are very close to it. Something like that. Are you happy with this, guys? It is fine if you don't understand things 100%. This discipline is like that. It's completely fine. This is just to tell you, if you open tutorials, they will just tell you that we will reduce the dimension, and that's it. Most courses will tell you that we can like afford to take the maximum, but they don't explain why in these cases, and we are like sliding, taking the maximum. That is when we slide, because like a cell and the other are overlapping in the number of pixels. So that's why we can afford to reduce the dimension. Do you have a feel of it, of what we are doing? Please tell me, guys. Are you happy so far? Are you happy, guys? Tell me, please.
For me, not 100% or not even maybe 60%.
You know what is the feature map and how we are computing it so far?
No, I missed the part. You know, I missed the almost 20 minutes or so.
Okay, yeah. If you missed it, that's normal. We can meet during the week and talk about it.
Yeah, I'll go through the video again. Yes.
Yeah, that would be very nice. Yeah. You guys, are you happy with this? And is Mahdiya still here? I think she's not with us. I was going to explain.
Yes,
yeah,
yes,
you're here.
I'm here.
Sorry. Yeah, you're here.
Yeah.
So that's why we don't need to detect the texture. You can see that the slide-in and pull-in, keeping only this value, we are. It's like an implicit texture building. If you can see that, it's like we have a lot of layers, each one specialized in something, and the other layer is specialized in something more complex, and we are sliding. As you can see, we are looking for certain features, and downsampling to remove things that are not useful for us. We keep only the maximum value. These combinations is like we are doing this texture detection. We are looking for text, but in a completely different way. It's not like because in image vision in the past we used to detect the texture with some clustering algorithms, and then we do the feature selection. Here, as you can see in CNNs, we are doing everything at the same time. Feature selection is detecting what shapes do we need. Then the combination of shapes is the textures. And then we have the fully connected layer that will do the classification. It's like all these 3 steps that we used to do in the past are combined together and learned automatically.
Yes.
And it is quite very powerful, a lot powerful.
Yeah, I think because the old method, we can't choose the best features. I mean, texture or about color or shape. Or
exactly. Yeah.
Even we combine all of them. But here, I think with the CNN, it's automatically.
It is looking by itself.
Yeah.
Yes. Yeah. In the past, we did more or less some manual feature selection, manually looking for features, and it was a horrendous task. It was very difficult.
Also, it depends on the nature of the image. So.
Yeah, I think we had also a method in the past where we had some kind of first layer CNN where we looked only at the basic features, at the edges, but not at the complex ones as we built them. That's why, like the first models, CNN models that were competing with traditional methods, they just blow the score up. The score just exploded.
Okay, thanks.
So this is the max pooling. This is the max pooling that we can see here. We take the maximum here, so we divide our matrix by 4 here. Max pool by 2 by 2 filters and side 2. That's what we use generally. Okay, shall I give you a pause, guys? I think I tortured you too much.
Yes, please.
Let's go for a pause, 10 minutes pause, and we will add. Yeah, we add just 20 minutes after that, and we close it. I think it was too much for today. Nah, let's come back in 10 minutes.
Thank you.
This conference will now be recorded.
Yes?
So just one question. Max pooling seems to be like PCA in terms of dimension reduction, because you can see the dimensions reducing.
Yeah, kind of, but it's simpler than that. It doesn't rely on the variance or so. It just takes the maximum for each number of points.
Okay. So in PCA, it's more about variance, whereas in max pooling, it's more about
yes.
In terms of points, you're saying.
Exactly, yeah. We can do the max pooling here because each point represents the same information. It's the same shape. So we keep the maximum because they all represent the same shape if it is present or not. It's like a bit like a zoom or a zoom in. It's like shrinking the image and keeping the maximums. Sometimes we can shrink the image by taking the average, but in this case we shrink the image by keeping the maximums. It's like the image is still there, but slightly different. That's the max pooling. Now let's see at AlexNet, one of the first CNNs that we got. This architecture won the 2012 ImageNet competition, and by a large margin. 50% error rate, and the second best was 26% error rate. You can see the difference. It's one of the first CNNs that was used. What they used the Relu instead of hyperbolic tangent or the sigmoid. I told you why the Relu was better. It is why is the Relu faster than the sigmoid? Tell me. Why is it faster than the sigmoid?
Because it's not binary. It's like.
But what makes it faster? Why we will converge in a fast way?
The activation function?
Yeah, it is. Well, the Relu is the activation function, but and the sigmoid is as well another activation function. But the Relu makes things much faster to train. Why?
Because we have the zero and the positive number. The gradient descent, actually,
exactly,
the
gradient. That's what I was looking for. That's the word. The gradient is better here, is higher.
Yeah.
Is of a high value, especially when it is positive. The sigmoid gradient is not good enough, and it can fall into what we call what? The vanishing
gradient.
Vanishing gradient, exactly. Because the gradient can be very small here in the sigmoid. And the Relu has a higher gradient. That's why things becomes much faster. They use dropout, if you remember dropout from last session or before, and they use the pooling layer, the max pooling here. So this is the architecture of AlexNet. It's named after the first author, Alex Krzyzewski. I'm not sure if I can pronounce it well. So what they have, they use in the beginning a big filter. You can see 11 by 11 pixels. How many activation map do we have here after learning this? How many activation? How many activation map or feature maps do we have?
96.
96, exactly. We have here 11, so the image shrinks because we have 11 by 11 from 22 to 24 to 55 by 55. It's shrinking. So 96 different shapes. Then we use the max pooling to reduce it, 5 by 5, max pooling of 5 by 5. So we take the maximum for each 5 values. So we end up with a very small tensor. Then, after the max pooling, I think the max pooling is applied directly here. From here we applied both the convolution layer and the max pooling. That's why we have 55 by 55. Then we use a different kernel now, a smaller kernel, 5 by 5. How many shapes are we learning here?
256.
Exactly. Now it's a bit higher. More shapes. And it is shrinking because it also has the max pooling. Probably a 4 by 4. Then we use a 3 by 3. You can see now it is shrinking. The more we go, because of the max pooling, it is shrinking more. But here we have even more complex shapes. How many do we have?
384.
Exactly. 13 by 13 because of the max pooling again, and 384 different shapes. This is more complex shapes, of course. Same here, and here it is. We are reducing it a little bit. We have less complex shapes than in here. So here you can see we have 1, 2, 3, 4, 5, 6 layers only for the convolution part. What shapes we are recognizing. Then after this, we use the dense layers that will take all the information here of these very complex shapes. This is like most complex shapes, combining them. And by these combinations, we can recognize what we have. Here we have 1,000 things here. It means we have 1,000 classes here. This is for recognition, taking all of these shapes, what we have, different shapes at different locations with all of this, and it will tell us what class is it. And this is one of the simplest architectures. Very simple one. And it beat the second best by a big margin. You can see here, it's 11%. 11% improvement is huge. Generally, before that, we had improvement each year, 1-2% better than the previous year. This is a competition where everyone brings his model and try to get the best scores. So each year, generally, it's 1-2% improvements. But here you can see the improvement was just insane. Was really huge. So it's like almost 10% improvement. Is it clear?
Yes.
Yes.
Yeah. Here, by looking at it from a bigger perspective, it becomes easier, simpler to see. Then we had AlexNet had 62 million variables, the number of weights. Sorry, this is even scarier. The number of weights is 62 million altogether here.
That's a lot.
Yeah, a lot. That's the problem with CNNs. They have a lot of parameters because of images, has like a lot of inputs. Then we had another architecture that did better than the previous one. This one is better than AlexNet with this dataset, ImageNet. And as you can see here, it's even a lot more complex. So we had here 64 filters and it doesn't show here what's the size of the kernels. I think it's probably 3 by 3. So we have here 2 layers of 64, then 128, then another 265, then multiple 512. So here we have 2 64 layers, 64 filters. Here we have 3 128. So this is 128, 128, 128 filters or activation maps. Same here, it's 256. They are shrinking because of the max pooling, as you can see. And here again, this is 512, 512, 512. Then the same thing again. But as you can see, the max pooling is not applied quickly. We put some layers, then the max pooling. 3 layers here, then the max pooling. They put 4 layers here, then after this, the max pooling. It's not like this one. The max pooling was applied most of the time in the beginning, but not here. It was applied like after each layer. Here, it's like we put some layers, then a max pooling. 3 layers, then a max pooling. 4 layers, and so on, until we get to the last thing. And this did even better than AlexNet. VGG, we had multiple, for example, VGG16 achieved 92% accuracy. This one, the error was 15%, which means it was around 25%. This one improved by 7%. Things. So it has 2 convolution layers, then a pooling, 2 convolution pooling, 3 convolution pooling, another 3 pooling, and then 3 dense layer. So we are done with the first part. Next time we are going to see like the most complex models. These are very simple models compared to what we have now. Now, like for example, GoogleNet or ResNet, DenseNet, they are a lot more complex than that. Huge like networks, but they basically use the same kind of layers, more or less, plus other types of layers. I wanted to present TensorFlow and Keras, but we don't have time. I will just show you for today the example. An example of training a network. or 5 minutes. Next time we are going to look at it deeply. So we are going to use this data set, MNIST. It consists of digits drawn. 5, 0, 4, like this is just a sample. So here we download it when we run this bit. Yeah. So we downloaded it. The shape of each image is 28 by 28. It is grayscale, so it has only one channel when it is grayscale. Do you agree, guys?
So the first layer will be 1?
Yeah, exactly. The first layer will have just one channel.
So, and we have like colored, it will be 3.
Sorry?
If we have like more colors, it will be 3.
Yeah, if we have more colors, the colored, it will be generally 3, yeah. Because grayscale doesn't require more than that. So we had, the dataset consists of 60,000 images for training and 10,000 images for testing. 60,000 are what we are going to use to train, and we are going to test the results on this 10,000 images. So to prepare the data, because the colors are between 0 and 255 for each pixel, the intensity, so a 0 means black, 255 means white. So what we do, we rescale them. If we remember data rescaling, we normalize to the grayscale color, we divide by 255 to get values between 0 and 1. So we get a matrix of the size 28 by 28, like this. Each image is 28 by 28. And when I divide things, values will be between 0 and 1. When we normalize 0, 1 here, or whatever. When we do the normalization, like here, we divide everything by 255. Then we build the model here. So you can see it's very easy to build the model. Conv2D, it's a convolution layer. What is the 3 by 3? Tell me. Can you guess what is this 3 by 3? These 2 3s?
It's a dimension that we start to compare with.
It's the kernel. So this is the image size. I don't know if you hear that. So this is the kernel. It means we take the filter, or the neuron will be connected to 3 by 3. So like this. Neuron will be connected to just 3 pixel by 3 pixels. Okay? Like,
so it's the filter.
It's the filter size, yeah.
Okay.
Like here, no, if I have an example, yeah, here. So this will be 3 by 3. What is this 32? Then what is it? This 32?
It's 288 divided on 3 by 3, 9.
No, it's 32 is the number of filters. So the number of neurons.
Okay.
So this is one convolutional layer, like here. It is one convolutional layer like this. We get 32 of this. So this first layer will learn 32 different shapes. It is this. If we look at the example, it is what we will get here. Here we will get 32 in this. How many neurons are we going to use here? 32, it means 32 different shapes. Activation equal Relu is very simple. This is, don't worry about this, it's a kernel initializer. How do we initialize the weights? And this is what inputs do we have? This is the input shape, which is this, 28 by 28 by 1. So this is a conv layer, a convolutional layer with the Relu activation. Each neuron is connected to 3 by 3, and it will slide along them, and it will produce 32 outputs. So we have 32 neurons. Is it fine so far?
But we didn't precise the stride.
By default, good question. By default, it's 1.
Okay.
We can precise it here. There is a stride, there is the what we call padding, but by default it's 1. Good question.
Okay.
So these are the main, because generally we use the 1 number all the time, most of the time, for the strides. So we have only one convolutional layer here. Flatten means that because it's we use it because the output will be something like that. These are my feature maps, and this is 2-dimensional outputs. So we have here 32, and here we have the size. We have the size. So we need to make them into one single array. Flattened just means we transform the 3D thing into one array, one-dimensional array. And then we connect it to what? We connect it to. We didn't, by the way, we didn't use the max pooling. It's one of the simplest network. We didn't use a max pooling. Then we have here a dense layer. What is it? Tell me. What is the dense layer? Go ahead. Don't worry of making mistakes. That's fine. Like I said here, after the end of convolutional layer, we have the dense layers. These ones. They take these shapes, complex shapes, and tell me what my class is. So we have like a fully connected neural networks here for the dense layer with 128 neurons. Then another dense layer. We use a little bit of dropout. Then another layer, dense layer with a number of classes. Here we have, how many classes do we have here?
16. I'm not seeing.
Well, the number of classes, we are trying to recognize numbers. Yeah, exactly. We're trying to recognize numbers. So between 0 and 9.
Oh my God.
Which means 10 classes. So here, the number of classes, we put it in here, which means we have 10 neurons, activation softmax. Softmax, I think Medea asked me about it, if she's still with us. I don't think she is. It's to say that we get only one class correct. It makes them as probabilities that sum up to 1. We will explain things better next time. I know I'm being too fast. We are going to stop, guys. And here we are using the Adam optimizer, if you remember it. We talked about RMS prop. We talked about how is it called? The momentum. Adam is a combination of these two. This is the loss function that we are trying to optimize. Accuracy is what we are going to show. Number of epochs, batch size. We did all of this, guys, if you remember. You remember vaguely, probably, these names.
Yes.
That's fine. That's fine. You remember vaguely, but it's a good way to recall them. So the number of epochs, how many tries we are going to use the gradient descent. So the number of iterations, basically. Batch size, if you remember, the batch is how many samples we use to train via backpropagation and the gradient descent. We said that the stochastic gradient descent doesn't use the whole data set. It uses just a portion. So here we are using portions of randomly selected inputs of the size of 256. This is the batch size. Do you remember this information, guys, with the stochastic gradient descent? Miriam, I remember you asked me about it. You asked me a question.
Is it me? It was me?
Yeah, it was you. You can't escape.
It's a lot of information. I need to go over it again.
That's fine. That's fine. Let's train it. This is a very simple, like as you can see, it's one layer, one conv layer of 32 filters, 3x3 kernels. The stride just one, then a dense layer of 128, then the output layer of 10 classes. Very simple one. We can draw it. Let's execute it and see how it does. We have a big data set of 10,000, 60,000, which is quite good, and 10,000 for testing. We are trying how many iterations? How many iterations we are trying, guys? 20. Let's try. By the way, you need a GPU to train things fast. I have a little GPU that can help me, but I'm not sure if you guys got some NVIDIA GPU that is good enough to train these things. Let's try. Let's go. No, I didn't get any. I think I haven't executed this maybe. I don't know what is happening. It's taking time. Let's stop it. Let's restart the kernel and start again. We are going to finish, guys. I know you are very tired.
I think we are giving you a very hard time, Reda.
No, I'm fine so far. Hopefully it's going to start training now. Yeah. Let's look at it is training. It's quite fast. So this is the accuracy on training. And this is the accuracy on testing, val accuracy. So you can see if it is improving or not. So the accuracy on training, we are optimizing this. The loss function optimizes this, and we can see if the accuracy on testing is good or not. They are almost the same, as you can see. Accuracy on training 98% and 98%. We quickly got good results, as you could see. This is with a very simple neural network, very simple CNN, because the problem is also simple. It's small images. So you can see accuracy on training is getting better, but on testing it's not improving much. We are a little bit overfitting. Now they both are not improving much. 99.5, a little bit here, but nothing here. We're not getting anything more in testing. By the way, 98 is not bad. It's not bad score. 98.5 or 6. So we got at the end 99.6 on training, 98.5 on testing. Like
it's good, not overfitting, no?
They're not a big overfitting. Mm-hmm. There is some overfitting, but the model is super simple.
Like 1%, no?
1% difference, that's all, yeah. The model is, yeah, exactly. The model is super simple. 32 here, 128 here. That's layer, and then it's just 3 layers. We have a little bit of dropout in this with this layer, and that's all. Here we have another model that is a little bit more complex. So we have 3 conv 2D, a little bit of dropout, then a max pooling. All of them I have 64 filters. All I have like 64 shapes, complex shapes, and they are stuck together. Then a dropout. Then 3 more complex ones, 128, with a little bit bigger kernels, 5 by 5. Max pooling and a dropout. So we have 3 layers. dropout and max pooling, then 3 more complex, bit more complex layers with max pooling and dropout. Then we flatten it, then a dense layer, same dense layer, and the output layer, 10 classes. I didn't change the parameter for Adam. These are the parameters. I'm using different parameters, by the way. What is the learning rate? Can you tell me what is the learning rate? If you remember, it's by how much we update the gradient, the weights, that variable multiplied by the gradient. If you remember, you had a variable multiplied by the gradient, and we modify the rate by this amount. So this is the learning rate. Let's train. So here the difference, I'm using a more complex model with many dropouts. I'm using the dropouts at many levels. Now you can see it is slower. I'm using a bit more epochs because it's a deeper layer. It's slower on my GPU. My GPU is not a top-notch one. So a more expensive GPU will be much faster. I don't know if you can hear, but my laptop is, my fan is almost going to explode now.
Do you have this daily then, Relu?
Daily what? What do you mean by daily? So you can see we quickly got to 98%. In the first epoch, we were at 96%. You could see with the other model, with the first epoch, we were at 96%. Here, even with the same batch size, we quickly got 90. Look at here. With 20 epochs before, we never reached that number. Accuracy on testing, 99%. So I'm going to stop here, guys, because it will take some time to finish. My best score here was at around 99.6% that I got in this with this data set. I think the state of the art is at 99.8%. The best score we were using the more complex models or other strategies to trade are at 99.8%, but 99.6 is not bad at all. You can see at the 3 epoch, I'm already at 99.33. It's even better than accuracy on training, which is weird. The accuracy on testing is better than the accuracy on training. Any question, guys, so far?
When the accuracy is in testing better than training, it means it's not overfitting, it's good, right?
Yeah, it's not overfitting at all, yeah.
Okay.
It's not overfitting at all, but at some point they will become very similar because we are optimizing this and we're trying to look at this. This is the effect basically of a little bit of more layers and the dropouts. The dropout can really improve generalization. Next time we are going to see more examples and we try more things. I know today it was a bit overwhelming. Sorry guys for this, but we are going to look at these things again more. Any questions so far?
I'm scared to overfit, you know, it's like, yeah, good.
No, here it's, I tried this multiple times. It doesn't overfit.
Mm-hmm. Okay.
Next time, this is like something I've drawn. I have drawn before, like a 3, 1. It's like an image, an artificial image that I created as a matrix, 1 and 7, and it was always able to recognize it. For example, before I tried with sample 3. Sample 3 is this one. It's like a 7 here, and it doesn't even exist. It's drawn by hands. If you look at the data set, 7 like this doesn't exist, and it was able to recognize it all the time. It said class 7. It's like this 99% is really real. It reflects how capable it is with external data, things that we didn't see. So we're already at 99.5, very close to the best score I got with this architecture. So thank you guys.
Thank you,
Any
Rida.
concern? I hope you are not scared, guys, or anything. Let's stop recording so you can see what you want.